Dr. Matthew Richardson, and welcome to another stream of CosmoQuest Astro Office Hours. Alright, guys, let me just take a quick moment to make sure things are working as they should work. Oh, okay, it works. Hey, Peter. Hey, Susie. Given that you guys are all saying hi to me, I'm just going to assume that you guys can see me and hear me just fine. Barely audible. Okay, that's not good. Let's check that out. Testing, testing. Okay, I'm looking at the mic and the mic settings on my OBS software, and it looks like it's working normally. All right, give me 1 second, guys. Can you guys hear me better now? Audio good in Texas? All right, so you're having good audio. OBS lies. I might have to start talking a little bit louder then. Is that better? Okay. Let's see if I can do something else here. Okay. Is that a little bit better, guys? Can you guys hear me better? All right. Okay. Let's just go ahead and get started. Um, Hopefully, whatever audio issues there may be, they fix themselves over time. Okay, good. Perfect. All right. So as promised, we were going to do an article review. And earlier today, I found an article that I thought would be very interesting. And it's related to the work that I did for my graduate studies with ultra high energy cosmic rays. And the objective of this article is to basically show the research that was done by some scientists to place an upper limit on the extragalactic magnetic field strength, as determined by their research using ultra high energy cosmic rays and the anisotropic distribution of these charged particles. Excuse me. Words are not coming out right now. Okay. So let's go ahead and just dive right into the paper. And I'm going to do things a little, well, not a little bit differently, but I'm going to give some background information so that the information within the paper makes sense. Of course, when these papers are written, they're typically written for a select few. That is, people who already know like the background information. So kind of already went over what the title is, and I'll break down some of the words in a minute. But this is a paper that was recently submitted to Astro PH or AppJ, excuse me, to the AppJ journal, and yeah, about 9 pages, 3 figures. That's not too bad at all. And so, to kind of give some background information, first off, what are ultra high energy cosmic rays? Well, they are charged particles that are produced by, at the current moment, unknown sources in our universe, and they exhibit really extremely high energies. I mean, if you were to compare the kinetic energies of these particles to actual macroscopic objects, you can see that some of these particles have energies that are almost close to kinetic energies that could be associated with, like, for example, throwing baseballs or footballs at fairly high speeds. So these are highly energetic particles that originate from sources in our universe. And one of the things that's very interesting about these particles is that if you were to look up into the sky, all directions into the sky, and look and try to map where these particles are coming from, what you notice is that they exhibit what's known as an anisotropic distribution, meaning that in one portion of the sky, the number of particles would be higher than in other portions of the sky. And so one of the major questions in cosmic ray and ultra high energy cosmic ray studies is, well, one, why is it that there's this distribution with the ultra high energy cosmic rays? But it makes it very difficult to determine this information. So again, guys, I'm kind of going through background here before I actually dive into the paper. Let's go ahead and switch the page up. Let's go back up. All right. So I was just saying that it's difficult to determine exactly why there's this distribution with the ultra high energy cosmic rays. And the reason being is because of the fact that these particles are charged. So the thought you should have in your head is that if you could imagine a source, any random source in the universe, that somehow is able to accelerate a charged particle to a really, really high energy, and then throw that particle or sling it towards Earth. Well, along the path in which the particle travels, initially, of course, you can assume it's probably traveling a straight path. Its trajectory will be slightly deflected. And the reason why it's going to be deflected is the fact that it's a charged particle, and that two, along the way, it's going to encounter magnetic fields. And so the good way of being able to think about this is the particle will encounter magnetic fields from one, within some sort of interstellar medium, or two, within the intergalactic medium. And to kind of explain what these are, the interstellar medium is basically the space inside of a galaxy, and the intergalactic medium is the space between galaxies. So I'm just taking a quick break to just look at the comments here because I don't want to miss any questions. Going back up top. And so to answer your question, Larry. So yeah, the OMG, or the oh my god particle was, if I'm not mistaken, a particle discovered some time ago. It was an extremely high energy cosmic ray. And so I believe it may have been a proton. And even if, well, I'm not going to say even if I'm wrong, but the reason why I would believe it's a proton, I remember reading the paper a long time ago, but I can't remember exactly what the composition of the particle was. But more than likely it was a proton, because protons are more abundant as far as the ultra high energy cosmic rays are concerned, versus other higher atomic number elements, such as like the iron nucleus, I don't think we'd have to worry about a uranium nucleus, because as far as stellar processes are concerned, I don't think any sort of particles or any sort of elements beyond iron are produced naturally in the universe. But to answer your question, it was more than likely a proton. Are they comparing the visual to their visual light sources? So for this particular paper, they are using data that was acquired by the Pierre Auger Observatory. So the Pierre Auger Observatory is based in South America. I can't remember exactly where right now, but it's based in South America. and its primary target are cosmic rays that exhibit energies higher than 10 to the 18 eV. And so for this particular paper, they've compared the the cosmic rays that have been wow that have been observed by the Pierre Auger Observatory to other studies that don't study cosmic rays but study other various extragalactic sources in our universe. Yes, never try to catch. Luckily, we don't have to catch them, right? Our atmosphere protects us from them, from those cosmic rays. They're really high energy. I wouldn't want to imagine what would happen to a human body if an ultra high energy cosmic ray actually interacted with one of the particles within someone's body. Oh, my background, right? um, if that helps. I mean, the idea is, of course, that you just have various sources, and the type of sources in which they can accelerate these highly charged particles are few actually. And there is, if you guys even get the chance to, you guys can always check out. Now, let's see if I can find a link for it. But there's something called the Helix criterion, which basically places a limit on the type of sources. Let's see if I can find it. Just like criterion. See if I can find a Wikipedia article for it. But basically, if you ever get the chance, of course, and I'm not quickly finding it right now, but it basically places a limit on the type of sources that can actually accelerate these particles, where that limit is the term, or where this limit is basically dependent upon the physical size of the source, as well as the magnetic field strength that the source can create. I'm pretty sure there's going to be some images, of course, on this, and yeah, like for example, this. I'm not going to get much into this. I'm going to go back to the article, but the key thing here is that, and I should note that there's many different ways in which you can determine or be able to place limits on the extragalactic magnetic field. This is just one particular way that this particular group of researchers used. And so, to kind of break down exactly with the actual picture and some math, a little bit of math, not too much, as to how this process works. Let's scroll down in the paper. We can imagine, let's see if I can blow this up a little bit more. So we could imagine that we have a source depicted here. Wow, what's up with my words? Depicted here in the upper left-hand portion of our image, traveling from the source to Earth. Or maybe not even traveling from the source to Earth, traveling in a direction that's not actually towards Earth initially. However, over time, as it propagates through our universe, it encounters it encounters magnetic fields from the interstellar medium as well as intergalactic mediums it will encounter, and these magnetic fields cause it to deflect. Now, for this particular paper, I believe that to be able to place their constraint, they're neglecting the contribution from the magnetic field that comes from the interstellar medium, and considering that the primary source of the deflection is due to the intergalactic medium. So basically, you have your ultra high energy cosmic ray ejected into the universe. It's flying. It's flying. It's flying. It's in the intergalactic medium. The magnetic fields there are causing it to deflect, and it deflects back towards Earth. encounters one of our particles in our atmosphere, creates a shower, and then a cosmic ray observatory like the PROJ observatory can detect the particle. Well, in this situation, they're basically just setting up the math they're going to be able to use to place or be able to calculate what the field strength should be. I don't want to go too much into this math. I mean, it's not too difficult to deal with. Um, so basically, they kind of work through the math here, where sine theta, the angle theta, corresponds to, going back to our image, corresponds to the angle theta that's in between our path of motion for the particle versus the physical distance between the source and Earth. So that's that angle theta. And then everything else, of course, is going to be d, which is going to be the path between the source and Earth. Z corresponds to, scroll over a little bit more, Z corresponds to the atomic number of the particle. For the most part, we can assume a proton, or anything from a proton to an iron nucleus, if you want to be able to evaluate the angle of deflection as a function of the composition of the particle. E is basically the charge of the electron times c, speed of light. B in this situation is going to be the magnetic field that's perpendicular to the flight path, and then E is going to be the energy of the charged particle. So of course, they go ahead and they solve for theta using the small angle approximation. So the general idea is that with these particular magnetic fields is that they're weak. I mean, extremely weak, actually. And so because they're weak, the amount of deflection is going to be small. Or we can assume the amount of deflection is going to be small. And because we can make this assumption, we can go ahead and apply what's known as the small angle approximation and solve for theta directly. And the solution that you end up getting is the one that you see here, where we're basically so basically the idea here is that if z was equal to 1, if d was equal to 10 megaparsecs, if the magnetic field strength, the perpendicular magnetic field strength was 10 to the negative 9 Gauss or nanogauss, and if the energy in this case was 10 to the 20 eV, you'd expect a deflection of 2.65 degrees between traveling from the source to Earth. Let's minimize this and get back some, make sure I'm not missing any comments here. And quickly want to make sure that I'm not missing, some good questions. A particle from millions of light years away with the force of baseball can be deflected. Yeah, right. Exactly what you're stating there, Hanny. And I mean, the deflection, of course, is over very small length scales. The deflection is not much. It's only when you're only when the charged particle is exposed to a uniform magnetic field over a very long distance. As you can tell by this equation, the particle, if a particle has 10 to the 20 eV and is exposed to a nanogauss magnetic field, it would need to travel, of course we're assuming the particle to be a proton, a atomic number of 1, it would need to travel 10 megaparsecs to be deflected by only 2.65 degrees. So it's not an extreme angle of deflection, but when you're thinking about over very long distances, that angle is pretty significant. Extremely significant, actually. Thank you, Larry. It's in Argentina. It's been so long. I mean, there was one point in time when I could just quickly remember that. A guy stuck his head in a particle accelerator? Oh, please do provide the link for that. I've never heard that before. I would imagine I don't see how that could be possible. Yes, Peter, there is no need to worry about it. Again, our atmosphere protects us from these really high energy particles, so and not just our atmosphere actually, our intrinsic, that is Earth's intrinsic magnetic field protects us from relatively low ultra or low cosmic ray energies. Not so much from the ultra high energy cosmic ray energies, but let's see. Hey, Artist Passion, welcome. Let's see. Making sure. This is a lot of comments I've missed. I apologize, guys. Yes, my stuttering is more than likely due to lack of sleep. I don't get much sleep nowadays. So, Adam, that is a very good question. So, roughly how many ultra high energy cosmic rays have been detected to date? So, a good way of being able to determine this. So, let me pop out the chat. I should have done that earlier, actually. A good way to be able to determine this, of course, is to find a very recent paper that shows what's known as an ultra high energy cosmic ray energy spectrum. And so, to kind of give you an idea of what this is, and of course, we're going to get back to the paper, but I just wanted to quickly answer these questions. Um, let's see. And to kind of help with my stuttering, it also might just be due to the fact that I'm trying to speak very fast right now. So let me actually just slow down a little bit. And that way I can stop with the stuttering. So of course we're seeing a lot of different a lot of different plots here. And they're all the energy spectrums for the ultra high energy or for cosmic rays in general. Um do, 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 do. Let's just go with this first one. All right. So a good way of being able to determine the number versus me just simply telling you, a good way of being able to determine the number of cosmic rays that have been observed to date, because honestly I don't know. And the reason why I don't know is because there are many cosmic rays observed at various energies. And so the way in which you'd want to do it, and I think I'm thinking about this correctly, is that you'd want to integrate the cosmic ray energy spectrum. So what I'm showing here on the screen is an example of what the energy spectrum looks like, where along the y-axis we have the flux of cosmic rays, which is basically going to be the number of cosmic rays per unit square area, per unit per unit area, excuse me, per unit steradian, which is basically an angular variable, and per unit time and per unit energy. And then you'd want to integrate this curve with respect to energy, as well as with respect to area and time, as well as over angle. And basically, that would basically give you your number of cosmic rays that have been observed over the entire range of energies that our current detectors can detect these cosmic rays within. But yeah, just to give a quick number, it would be just difficult to say. I can probably give you a number for a particular energy, but yeah, it'd be very difficult. At the highest energies, though, the numbers aren't high at all. It's on the order of probably like tens to 100. No, tens. On the order of probably tens, maybe 100, low hundreds. Okay. But yes, as Larry is stating there, most of the ultra high energy cosmic rays are thought to originate from outside of the galaxy. Um, a lot of that's due to the fact that many of the cosmic ray studies show that the distribution of cosmic rays, this anisotropic distribution, is oriented such that many of the cosmic rays are coming from directions that are not within our galactic plane. So it's thought to believe that many of the particles are coming from extragalactic sources. And there's other reasons as well why we think they're coming from extragalactic sources as well. So okay, so to get back to the paper, so they basically use this diagram to be able to calculate what the field strength would be, or the angle of deflection. And of course, from here, you can be able to calculate what the field strength would be just by solving for B. And so I'm going to scroll down. I'm going to skip up a lot of this math. We're not going to get caught up into trying to explain all the math here, but go primarily to the main result. Scroll down, here we go. Because of course the overall objective of this was to be able to place a constraint on what the field would be. And so what we're seeing here in this particular plot is along the y-axis the magnetic field strength of the intergalactic or extragalactic medium as a function of coherence length. So one of the things I left out earlier was that when as the particle travels through the intergalactic medium, it will encounter, let's just say, two different types of magnetic fields. One type of magnetic field would be more turbulent. That is that the orientation of the field is random, versus a more uniform or coherent field where you can imagine all the field lines are, for the most part, over some particular length, oriented the same way. And so in this particular paper, I believe they end up accounting for, or in their calculation, they end up primarily considering, of course, well, this would have to be considering the field, assuming that the field strength is coherent over some length. That is, that the field strength is oriented a certain way. And so in this particular plot, the key things to note are that the gray region corresponds to combinations of magnetic field strength and coherence length that have been deemed to be rejected. Therefore, we wouldn't expect to find a field strength of, for example, 10 to the negative or a nanogauss at a coherence length of, let's say, 10 to the negative 10 to a parsec, which would correspond to 10 to the negative 6 megaparsecs along the x-axis. But this particular plot has actually been composed of different studies. And honestly, I can't really talk a lot about these other studies, but they've placed their own constraints on what the extragalactic field strength can be as a function of coherence length. There's this one particular study, the MHD turbulence decay study, as well as studies from gamma ray observations. The Hubble radius is actually a constant. It can be calculated. I'm trying to remember exactly what the calculation is. It's going to involve using the Hubble constant, which is going to be in units of per time velocity. I believe it's going to be the Hubble constant times, or maybe I believe it's the speed of light divided by the Hubble constant, which would give you the Hubble radius. But basically, they're saying that you wouldn't expect for coherence lengths to be larger than the Hubble radius. And then there's the CMB observations that have also been able to place their own constraint. And so what they've basically added to this particular plot is they've lowered the maximum field strength that's achievable, that can be achieved by the extragalactic fit medium, somewhere in between the coherence length ranges of let's see, roughly around, I want to say 10 to the negative 1 megaparsecs to about 3 times 10 to the 3 megaparsecs. So the galactic magnetic field is going to be basically a contribution of stars, as well as as well as galactic fields that can be generated by like black holes and stuff, by supermassive black holes at the center of the galaxy. And would it be all jumbled up? Um, well, over certain length scales, the case could be that the field can be coherent, meaning that it can be oriented such that it's the orientation of the field lines are all within the same direction over certain lengths. What they resolve just with better Cepheids. So in this situation, what they've done to be able to place their constraints is they've used the work that the Pierre Auger Observatory has been doing in detecting these ultra high energy cosmic rays, and the they've compared them to the distributions of extragalactic sources as determined by a few other um a few other observations done by I saw something earlier in this paper. Here we go. As determined by the 2MRS study, as well as the Fermi-Lat study, Swift-Bat study, and they've been able to determine what the field strengths are based off of these studies. And in doing so, they were able to go ahead and modify this plot to be able to, of course, the highest constraint that they were able to get was, or the best constraint they were able to get was based off of assuming that the z values of our particles was 1.7. I think this is the dotted one, or 5, excuse me. Oh, okay. But basically, that's the general gist of what's going on here. Is that they've actually just taken the results from other observations, and based off of their work, they were able to better get a better sense, or no, to place more stringent constraints on the magnetic field strength within a particular range of coherence lengths. So anywhere that's below, let's see, anywhere that's kind of below, I want to say somewhere around maybe like 3 to the negative 10, or 3 times 10 to the negative 1 megaparsecs. Anything that's below that, they're not really placing any new constraint as an upper constraint on the field strength, because MHD turbulence simulations have already done that. But anywhere beyond that, all the way up to the Hubble radius, they've been able to place more stringent constraints on the field strength. And so that's pretty much it for the paper. And again, guys, I'm not about to go through all of the math here. Much of this math that they have here is basically just going to be related to the initial equation I showed you earlier. So that was pretty much it, what I wanted to talk about as far as the article review is concerned. For the remaining portion of the stream, I'm just going to go ahead and focus primarily on some of the work I'm doing right now with CosmoQuest. And in the process, I'm going to go ahead and answer questions. So in my particular work with ultra high energy cosmic rays, the objective was to be able to determine if we could detect these particles through within the microwave regime of the electromagnetic spectrum. So the idea is that as the particles come in from space, they interact with particles within our atmosphere and cause what's known as as air showers. And basically, these air showers are composed of particles and light. Primarily particles, but the light is the light that's being produced from the showers is also it's due to the fact that the particles are due to particle interactions. Yes, artist passion. I'm not done with my explanation. I'm going to get back to that, but yes, I've switched over to C++ programming because I'm going to primarily focus on that now, which is the work I'm doing with CosmoQuest. But yeah, I want to give a better explanation of what I was just doing with that, and that is that particle comes in, and it is ultra high energy cosmic ray comes in, it hits a particle in our atmosphere. This initial collision will produce a shower of particles. Um, and as the particles propagate through the atmosphere, what you end up getting is kind of like what's known as like a weak plasma. And so you can have interactions between now what you'd have free electrons, or I believe it's actually I'm sorry, I just keep seeing questions coming in. Muons are one of the particles that are produced within the shower, and they typically begin to get produced once pions have hit like a critical energy. That is where you stop making more pions, and the pions have a chance to actually decay into muons. But to get back to what I was saying, basically when you get this weak plasma, the weak plasma can have interactions occurring within it or the theory is the weak plasma can have reactions, can have interactions occurring within it that can produce microwave emission. And so the overall objective of my research was to use microwave detectors to see if we can detect this emission from the showers. And the overall result was that it couldn't be detected. If it was occurring, it was not being detected by our detector. All right. So what I'm kind of doing now with my code here is I'm just moving some things around so it'll be a little bit clearer if someone were to come along and start like looking through it. So I'm not actually doing anything new. I'm just moving things around so that it'll make a little bit more sense. So, okay. I move that around. And this is all a part of the incidence angle analysis I've talked about in previous streams. Um, I don't think I'm not doing anything new. I'm just like I said before. I'm just like for example, I have a plotting package, and I want to make sure that this plotting package only does plotting. It doesn't do any sort of analysis. All it does is take the numbers that have been generated by other functions and then just simply plot those numbers. Yeah, there has been plenty of times when I've had to like take someone's code and kind of like decipher it, and it's hard to decipher because things are all over the place or there's no comments. In this situation, much of the functions that actually do work, like do analysis of the numbers, are within the utilities package. Hmm, I think I want to change this too. Let's make a new one. Oh, Hanny, you are so right. It kind of sucks if you come back to your code years later, even though you wrote it, and just can't understand what it's doing at all. There was a point in time when I used to have that issue, and that was because I wouldn't comment my code. Let's see, I want to find not total, but find different. So, Adam, are you talking about? Of course, you're talking about the highest energy um, cosmic rays. But what's interesting though is that if we are able to actually determine a source of ultra high energy cosmic rays, even if it's just one source, because at the moment we don't know of any sources, the next step, of course, is that once we've determined that that is the source, we need to then determine exactly how is that source accelerating the particles. Oh, I am so sorry. I'm just working here. I'm not explaining what's going on here. So I've kind of like I've switched over completely from what I was talking about. I'm actually working on my incidence angle analysis, and so to explain that, um, this is one of the projects I'm working on with CosmoQuest, where we are trying to determine if the incidence angle on the lunar surface, that is, if the sun angle, the angle at which the sun hits the lunar surface, affects how our citizen scientists are identifying craters. And so one of the things that we need to be able to do is take the images that we have of the surface of the moon that have been marked by many users and see which of those images show overlap. Now note that the images that we have, some of them are the images that we have, some of them are come from the same, what I'm going to term to be the same global image, which means they're images that come from the same mass bigger image, but they have overlap because of the way in which we've cut up the master images, the global images. Wow, this is not coming out the way I want it to come out. But basically what I'm doing here though is just making sure that I'm able to determine which images overlap, whether they come from the same global image or a different global image. I want to be able to determine which images overlap. That way I can go ahead and extract information such as the user marks for a particular image for images that overlap one another. And that's kind of what I'm focusing on right now with this function is being able to work on, which I've already done. And again, I'm just moving stuff around. But this particular function that I'm working on right now will allow me to be able to find all overlapping images that are at different incidence angles. Which another way of saying that is find all overlapping images that come from different global images. All right, let me see what you're looking. Oh, okay. I'm also showing my terminal there. All right, so see if I can scroll up here. So basically, the idea here is that each entry. So we're looking at a vector. A vector that a vector that I've created that shows all the important information that I want to know about two overlapping images. Where this first line, I'm just going to kind of scroll to make sure you can only see that. This first line that I'm showing here is basically just all of the column headers. And so going from kind of left to right, if we were looking at this at the entries for each column, we have an ID number, which basically is just the ID number for the match, for the images that have been matched together. The second column would end up giving us the name of the first image. It's personal image ID. The next column will end up giving us the horizontal resolution of image one. The fourth column will end up giving us the vertical resolution of image one. Fifth column is going to end up giving us, as determined by the coordinate system that I've established within my analysis code, would end up giving us the position of the lower right hand corner of image one. And then basically we're doing the exact same thing in the fifth column, but this is going to give us the x position of the upper left hand corner of image one. Or just basically, actually, I'm sorry, that's wrong. That's completely wrong. Fifth column is going to give us the x position of the left edge. The fifth column is going to end up giving us. Sixth column is going to end up giving us the position of the right edge. Sixth column is going to end up giving us the y position of the low edge, and then the eighth column. I'm getting my column numbers mixed up here. The eighth column is going to end up giving us the Y position of the upper edge. Then I go on to give the image 1's height, which is basically the difference between the Y high and Y low for image 1, the width, the difference between X high and X low, and then the image area in the area. Of course, I don't have to add these columns because I can calculate them somewhere else in the code, but it's just easier just to be able to see it without having to do the calculation in my head or having to do the calculation multiple times. And then I repeat the same thing with the next several columns for image 2, and then I provide information about the overlap area as well. The position of the edges of the overlap area between the two images. Yeah, sometimes I find it one of the hardest things that I've found about science is being able to describe something that you know to others. It can be so difficult at times. All right, so objective here, basically just to clean up my code. And so right now I have already written this function, but I need to add it to the utilities package. So where do I want to put that at? It's another thing I like to do with my code is make sure it's alphabetically ordered. Let's see, I think I could just do this. And now I can go ahead and add this above line overlapping. Okay. So yeah, all I'm really doing now, guys, is just, like I said before, moving some stuff around. This function was initially within my plotting package, but again, I don't want my plotting package to have functions that analyze the numbers. Let's see. But I do want to have the ability to be able to plot whatever analysis that's been done. And so let's see, this is going to be different incidence angle. Different incidence angle of statistics. Yes, you're so right. Raptor, you're so right. I'm just going to go by that last part there. And of course, I am still working on it. I mean, golly, am I still working on it? If someone's describing something to me, or if I'm like reading something, I have no problem with being able to understand that information. But typically, when someone else comes along and they have to ask me, okay, can you describe this to me? Certain things I can describe with like relative ease. Other things, it takes me some time to be able to describe it the way I want to be able to describe it. Let's see. And really, I've just discovered that not just discovered, but I know that the way in which you get good with being able to share science with others is just by doing it over and over and over again. Which is one of the reasons why I love this stream. Um, it's a great chance for me to be able to explain things and to get real feedback. If someone thinks I'm not doing something good, I mean, by all means, guys, just tell me, like, Matt, that's not making sense. Try again. And I will definitely try my best. All right, we don't need these. That's all part of the plotting stuff. The same here with in bins. We can get rid of that. We don't need the plotting information. oh, Haney, that's a great question. Oh, that is a great question. Honestly, whenever I go to explain things to my relatives at times, they're like, it's boring. I don't want to hear it. I try my best to make it fun too, but some things they find interesting. And the things they find interesting, they can remember. But the things that bore them, they're like, I don't want to even hear it. But I also think that just being able to simply explain something to someone, even though you could be giving the perfect explanation, I think it's also just as important to make it interesting. And I've said this in a previous stream, but I had a professor um, who taught physics in undergrad for me, and of course, he knew everything. I mean, he could easily explain this stuff because he had taught the class several times. It's just that he had this perfect monotone voice, and it would always put me to sleep. But for the things that came off to me as being interesting, I could sit there and listen and have no problem, like quite literally repeating whatever he said verbatim. Yes, yes, Raptor, you surely do. And honestly, guys, I mean, I know that I'm here to kind of like bring science to you, but these conversations that we have, I honestly look forward to them. Let's see. Astro, you're so right. You're so right. You're so right. I am very much still very much working on being able to communicate my science in a clear and coherent manner. And I'm a long ways from doing that, but I'm working towards it though. A professor once told me that if you could just explain the science you do like a story, it would come off as a lot better. Well, you'd be able to better communicate that science to others. Okay, I've been stuck on this one line. All right, so the objective of this, of course, is just basically be able to just find overlapping images that are different incidence angles. Do I have that already set up? No, I don't. So this needs to be OI. Plot. Good. I no longer need this anymore because this isn't plotting anything. I can delete it here. Of course, I no longer need the canvas information, nor this, or this. Can get rid of all of that. Oh, wait a second. Did I remove something I shouldn't have removed? Oh, this part. So within the process of filling the histogram is where I'm actually determining overlapping images that have different incidence angles. So let's go back here. So this is the exact reason why I need to do what I'm doing right now. I've entitled this section of this particular function, I'm filling a histogram, but it's doing more than just filling a histogram. It's actually extracting data that I want to be able to extract. So let's retitle this as extracting overlapping images that are at different incidence angles. But yeah, guys, do any of you guys stream? I know a few of you stream. Because every now and then I like to come on Twitch and just see what other people are doing. Yeah, I need to start coming and see what you guys are up to. Because, I mean, a lot of you guys are always here supporting me. And like I said before, although I'm here to bring you guys science, I mean, you guys are important in my professional development and being able to communicate the science I know. Okay. Headshot for good. I'm going to add you. And Uncle Bill Jordan, even if you're hosting, I mean, I still want to come see what you guys are up to as well. I know I've stopped by on a few of Noel's streams. Let's see. All right. As well as you, Adam. Just let's see. Is there an easier way to do this? Let's see. Okay, that's so much easier. Okay, that's. I think I already got everyone else, did I? Okay, good. Well, guys, the time is now 1:30 p.m. And I think almost in like 30 minutes, will there be astronomy cast in 30 minutes, Susie? So yeah, I'm gonna go ahead and log off now and continue doing what I'm doing right now, but then I'll see all you guys during astronomy cast. Alright guys, thanks for stopping by. I will be back again next Wednesday after Daily Space News at 12 o'clock p.m. Central Time. And I look forward to talking to you guys then. Alright guys, bye.